Hello, everyone. Welcome back to now lecture 13. So, we're almost halfway through the semester. So, glad everyone is sticking with it. Okay, so today we're talking about, we're now going to talk about more thermochemistry and how we use the concept of energy for chemical reactions. Okay, so first let's talk about something called specific heat or specific heat capacity. So, you may have encountered, specific heat or heat capacity of a substance. Um, so, heat capacity, usually we don't talk about that much here, but heat capacity it does depend on the amount of substance. But in chemistry, usually we worry about the specific heat capacity because that's independent. It's a quality that's it's kind of like density, right? So no matter how much water you have, you know, 1 mil of water or 5 mils of water, the density of the water will be the same. That's the same thing with specific heat capacity. Okay, so for our focus, we're going to focus on specific heat capacity and not heat capacity. Okay, all right. So the first thing we want to go over is how did we observe this concept of heat capacity or specific heat capacity? Well, so an experiment done by Joseph Black in the 1700s, he showed that when you take two liquids at different temperatures and you mix them, um, he saw that he saw a peculiar he saw some change with the temperature, and but he didn't also note that there's a temperature change. It also depended on the substances being mixed as well. Okay, so in our so what he saw was that if you mix, so let's just go through this little the results here. Okay, the amount of heat. Um, so as you see in this picture, right? When we combine the two temperatures at 150 degrees and 100 degrees Fahrenheit, eventually the temperature of the water is kind of like right in the middle. And what we can say is the amount of heat lost by the water sample at the higher temperature was equal to the amount of heat gained by the sample that was at 100 degrees Fahrenheit. So the mixture temperature was an average of the two values, right? Okay? Yeah. But what if we combine water at a lower temperature and now a different substance, mercury, at a higher temperature? So, what this now, see here, we get a temperature value that is 10 degrees less than when we mixed when both of the substances were water. So this kind of tells us that mercury and water, they kind of interact with heat differently. So now let's kind of go over that. So when mixed with mercury at the same temperature, the temperature of water changed less because we say water has a larger capacity for heat, meaning it takes more heat to produce a temperature change. So you know how you boil water, it'll take a longer time for water to boil. So that's why it usually takes, depending on how high you can heat it, it'll take a long time or a short time. But usually water has a really high boiling point, so it takes a considerable amount of time to heat to a boil, right? So we could say it takes more heat to produce a given temperature change, right? Okay. So then by this measure, we say, okay, mercury has a lower capacity for heat, so it takes less heat to produce the same kind of temperature change for the mercury. Okay, so this is the concept of heat capacity. The capacity for heat and amount of matter determines the temperature change of a substance when it is heated. Okay, so the capacity for heat and the amount of matter, well, I just said that. Sorry about that. We can then define this as the specific heat capacity of different substances by this definition here. Okay? The heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So that's the definition for specific heat capacity. Now, the units for specific heat capacity are usually either one of these: calories, so cal means calories per gram, dot degrees Celsius per degree Celsius here, or you could represent it as in Kelvin, so cal per gram Kelvin. So there's two ways we can do this. Okay, so this would be the units for a specific heat capacity: cal per gram degrees Celsius. So calorie is a energy unit. Cal is a unit of energy. So you may have heard of calories when talking about food calories. That's where the energy unit comes from. Food has a specific energy content, and usually we represent that with a big capital C cal. So they're different. So calorie is kind of the base unit, and then calorie, a food calorie, is 1,000 calories. So it's like the kilo unit. Okay. So we can also describe the heat required by, thinking about per mole of a substance by 1 degree. So this is what we call the molar heat capacity. So the molar heat capacity is cal per mole dot degree Celsius. Okay? Or we could say cal per mole unit Kelvin. So that's the molar heat capacity. So here are some energy units. So nowadays, the approved unit of heat is the joule. So 1 calorie is equal to 4.184 joules. So kind of keep this unit in mind because we'll be using this a lot. And 1,000 joules is equal to 1 kilojoule or kilojoule. So kJ refers to kilojoule. Okay. So now we can replace calorie in our specific heat unit with joules. So it will turn into joule per gram degrees Celsius, or joule per gram Kelvin. And also we can convert this to also the molar heat capacity: joule per mole, mole Kelvin, mole degree Celsius, and joule per mole degree Kelvin. So you can expect these different units. You may see either of these. Okay. So sometimes the energy will be represented in food calories. So a big calorie is a capital calorie. That's what we call food calories. So the conversion is 1,000 calories, okay, equals 1 calorie. So this is also called a food calorie. And this is also equal to 1 kcal. So yeah, those units are pretty much the same thing. Kilocalorie, big calorie, same thing there. But the important thing is that the calories you see on food labels is a kilocalorie. It's not the small calorie. That would be too small. So the calories that are in food, they're actually on a pretty big scale. Because if you think about it, the food we ingest, there's a lot of it, so it should probably be on a large scale. Okay. So now let's answer this question. Why does mercury change temperature faster than water? Okay, so let's kind of go into this. So let's kind of go deeper into this explanation here. So when heat is absorbed by a substance, there is often but not always an blank in the kinetic energy of the particles that make up the substance. So there's often an increase. But this is not always the case, and I can't really think of an example when this isn't the case. But maybe there's such a small temperature change, or you apply heat very instantaneously or like a very short period. There probably won't be an increase in the kinetic energy. But usually, when things heat up, there's always an increase in the kinetic energy. There's often, not always. Okay. All right. So, absorption of equal amounts of heat by equal moles of substances will increase the temperature. Temperature of the substance, okay, will increase the temperature of the substance. So let's see here. Increase the temperature of the substance. Okay. So what we should so which one will increase more, right? So you think of it this way: the one with the heat capacity. When we say heat capacity, it could be kind of misleading. So what you should think about is that it's how well it can handle heat, right? So the substance with the lower molar heat capacity, right? The temperature of the substance with the lower molar heat capacity will increase more than that of a substance with a higher molar heat capacity. So that's why in this case, the temperature is closer to the water's initial temperature because it took more energy. It takes more energy to increase the temperature of the water. So that's why it didn't increase as much, because mercury's is less than water. And so that's why it decreased faster. Okay? All right. All right. So let's move on here. So we could say substances with a high molar heat substances with a higher molar heat capacities, or let's just say substances with high molar heat capacities require more thermal energy. Okay, more thermal energy to give their particles increased motion. Then those with a low molar heat capacity. Okay, so the higher the heat capacity, the harder it is to change the temperature of the substance. And the ones with the lower heat capacity, it is easier. That's why metals, they usually have low heat capacities. That's why they heat so fast. So that's why they heat so quickly, and you should never handle metals, any metal containers with your hands, because they tend to heat and cool very rapidly. Okay. So here's a table with the specific heats and molar heat capacities of common substances. And these are given in units of joules per gram / mole, unit Kelvin. Okay. Here we go. So see the metals here, they typically have low heat capacities. Copper being having a very low heat capacity. And then non-metals like gases, they tend to have low heat capacities as well. Mercury has one of the smallest heat capacities on this list, pretty much. And then water there is the highest with 4.18. And you can kind of see that, and the molar heat capacity is pretty high. Okay. All right. So now let's do this exercise here. Talk about heat capacities. Okay. Okay. If 10 moles of aluminum, copper, and iron absorb equivalent amounts of heat, which one of the metals will experience the largest increase in temperature? Okay, so let's go back to our list here. So we got aluminum, copper, and iron. So aluminum, copper, and iron. Okay. So let's just keep those values in mind here. 0.9, 0.38, 0.449. Okay. So which one we expect the largest increase in temperature? Okay. Oh, okay. So we shouldn't think of grams in this case. So we need to look at moles. Because I was confused for a second. So wait, the aluminum has like the highest. So we have aluminum, copper, and iron. So just don't think, oh, so if they have if the specific heat capacity in grams is lower, the molar should be the same. The same trend. It's not always the case. So we have to think about, both the values in moles and in grams. They're not always. There's not always going to be a consistent trend in this if you go from grams, say moles for heat capacity. Okay, so if we look at this list here, we see aluminum has the lowest molar heat capacity, right? So remember, the temperature changes the fastest for the element or substance with the lowest heat capacity, lowest specific heat capacity. So in this case, aluminum will have the largest increase in temperature maybe I should expand on that because it's more heat capacity cm is the smallest. Okay, so that will be the smallest. So aluminum is will have the largest increase in temperature because it takes less energy to increase its temperature. So that will have the largest increase in temperature. Okay, so that is specific heat capacity, molar heat capacity. All right, let me just fix this parentheses here. It's kind of bugging me. All right, CM. All right, so okay, so let's stop there and we'll pick up how we use this quantity, the heat capacity, in a chemical problem. Okay, so we'll pick this up in the next video. See you then.